So, welcome to this explanation of FastFlood, the model and the platform around it, and the way that we are able to provide some of the most detailed flood information globally out of the box for users. And on top of that, provide interactivity and adaptation options, real-time sketching of measures to reduce flood risk as well. My name is Bastian van den Bout, and I'll be talking today a little bit about this model, how it works, what you can do with it, and then I'll show you some real examples near the end as well. If you want to try it out or follow along, we also have the model available at fastflood.org, and everybody can try it on the website there. Now, the philosophy behind the model is that we're trying to do global information in a very easy to use way. And on top of that, also provide interactivity to the users so they can not just look at flood information, but also play around with it and sketch alternative scenarios. We do this globally, so you can do this anywhere on Earth and get flood information at high detail. It depends a bit on which country you're in, what level of quality we can go given the availability of national level data sets. You can do detailed forecasts using weather forecasts as input data automatically. We go up to 1 meter resolution for countries where we have the data to support this. You can do both historic events, so flood maps for the past, but also look at potential future scenarios with and without climate change. And as I said, it's all fully interactive. And this combination between global out-of-the-box availability and interactivity is giving a lot of new opportunities in the fields of engineering and planning, early warning, but also insurance and assets management. Before we dive into how it works, I want to show you very shortly also what it is. So this is just a quick screen recording. You can go right here to the website and then pick a location anywhere on Earth. Select a scenario, whether it's a moderate or an extreme or a forecast, and then quickly get a detailed flood map for your location. Now, you can toggle the 3D view to see also the overlay with building elements and sample the flood depth for those individual buildings. As I said, it's all interactive, so it's collecting the data and running the model on the fly for you in several seconds. So you can also add barriers like I'm doing here, and then run the model again, get a new flood map output that takes into account the changes that were made by you, and you can compare them then side by side. Now there's a lot more detailed options you can go into with the tool, like showing specific return period maps or hazard analysis. But for now, we'll look a little bit as well at the forecasting options. So using as input the global weather forecasts, we can take any area on Earth using this system and provide the forecast data as an input and simply specify we want a forecast for this particular region. Now you can tweak some of the settings here, but you don't have to. By default, it's going to look at the peak flood depths for the coming days for that area. Here we see in 4 days some severe precipitation coming in, and then we get a flood map output as a result from that simulation that we just did. So this flood map is a forecast map for the coming days. Now there's lots of analysis options there, and you can share simulations with others, look at exposure, etc., etc. So let's start a little bit with the basics, right? So how does this work? Because flood modeling traditionally is quite an involved process between data collection and preparation, and then the model itself that can be quite demanding to run. Up to weeks and sometimes months of simulation time to do detailed modeling for specific areas. So how are we able to get this all together within such a short time span? Now, there's mainly 3 parts to that. The first one is the input. We do a lot of pre-processing at a global scale for detailed input data sets. So we make sure they're pre-prepared and ready for the user to use in a model domain of their choice. And that includes things like topography, so the elevation of the landscape, climate, both historic precipitation data as well as climate change scenarios, information about the nature, presence of forests and shrubs and agriculture, but also the soil itself and how much water is going to infiltrate into the soil during such an event. Buildings and infrastructure, information about where buildings are and how that impacts the hydrological behavior of the area. And then rivers and channel information as well. Most of these use some space-based global data sets to supplement the data in areas where we don't have national high-resolution data sets. That helps us get that global coverage. And in some of them also we use AI to try and improve the accuracy in terms of the values that go into the model. Think about the topography, think about the climate precipitation analysis, especially in areas where there's very few stations available. The AI bias correction procedures that we developed help improve the quality there by learning from stations worldwide. Now all of that data goes into this modeling core, and most models, they follow the hydrological cycle. So you have start with precipitation, falling, and then some is caught in the leaves, some goes down to the ground, and then some infiltrates, some goes into the groundwater, some forms runoff, and eventually that all accumulates in the rivers and becomes flooding. Now we do a fully physically based hydrological modeling with a two-layer green and amped groundwater component, and then our flood simulation comes after that. Now, the flood simulation itself is quite different from traditional flood models, which is where most of the speed gains are, and we'll dive into a little bit what that means and how that works. And then what comes out of the model is flood maps or hazard information and exposure as well. Now, the way the model itself is as fast as it is because we deal with predicting directly the peak parameters. So we typically don't produce an animation of the flood event, but instead we directly calculate the flood map with every location featuring the highest flow height that would be expected during the event. We also have some numerical tricks that we rely on, like cascaded grids at different resolutions to help us do the relevant processes at the most optimal level of detail. And we separate routing from inundation calculations internally in the model behind the scenes. But mostly the time saving is due to the fact that we directly calculate the peak parameters. Now you might wonder, how can we skip the time stepping that's often required with flow modeling and do this effectively? Just in summary, these are sort of a rough outline of the steps that are involved in the model. There's some particular data correction and pre-processing that happens at the start. This is step number 1. Predominantly, we do a fast sweeping version of an hydrological terrain correction, where we deal with hydro-cutting, hydro-filling, and generally improving the terrain data. And a byproduct of this is that we can make a routing network. And in step 2, we use this routing network to generate a steady state flow network for the domain. Now, this steady state flow basically is sort of a final state. If you had a constant rainfall, that would happen infinitely long. That's not something that you see happen in reality at the scale of watersheds or river systems. So we do a physically based calculation of what the non-steady state but actual flow should be. Then in step 4, we sort of inverse and go from peak discharges that we have estimated in step 3 for the entire domain. We go back to flood depths in step 4 and 5. For step 4 and 5 in particular, we do a traditional hydraulic calculation using the same Van equations. But before that, to speed this up, we use what we call a pressure reconstruction using logarithmically cascaded profile approximations. This helps us convert from discharge values to flood depths within the floodplain. There's a lot to that, but I'll refer you to the paper if you want to read more details on this. In the end, this allows us to switch very rapidly from discharge to flood depths, and we see excellent behavior in case studies, in this case both in the Netherlands in the Rhine and in Koshi River in Nepal, where we looked at output from hydrodynamic models, fast flood, and then Manning's engineering style equation for states discharge relationships. Now, there's a lot more complexities to setting up a model that can work for any domain globally, whatever the user selects, right? We have to deal with all these different types of data layers and merge them together in the right setup for the model domain that the user selected. And then we might also see that the user selects a model domain, and there is a very big river that comes in into this model domain. Now, that gives us an issue because we are not collecting all of the data for the basin that's upstream, the entire river system upstream of that point. So what we do instead is we provide boundary conditions. These boundary conditions, they feed water into the model domain at the edge of it, and that helps us deal with incoming water from riverine systems that are large and coming in to the simulation domain that the user selected. These boundary conditions can be set by the user, but can also be set automatically. So there's sort of a no intervention automated setup as well. You can use them yourself also to do dam break scenarios, so where you specify flow outflow coming from a reservoir or some kind of infrastructure, and want to look at the hydraulic behavior downstream of that point. We've done this successfully for dam break type events, like what happened in the Kazakhstan floods in spring in 2024. We estimate peak flow rates either based on measurements or on physically based relationships dealing with reservoir properties. So that gives a little bit of an overview of how the model works behind the scenes. Now, I want to talk a little bit about some of the tooling and usage that we have available around the model, mostly around FastFlood Global, our latest platform. Now, the main first usage that you'll see for the platform is sort of an out-of-the-box baseline of flood hazard information. So you can select a location anywhere on Earth, select a scenario, whether that's a forecast for the coming day or 3 days, or whether that's a potential future disaster that could happen. And here we often talk about probabilities. So we talk about the yearly probability of occurrence, and often that's phrased as a return period. So a 100-year return period event is quite an extreme flood that would happen once every 100 years on average. Now, it doesn't guarantee that in the coming 100 years such an event is going to happen. It's just a probability. So it's like tossing a coin and saying, look, we have a 50% chance that we're going to see heads. But in reality, you could throw heads 4 times in a row. Although exceedingly unlikely, it can happen, right? It's probabilities, it's not guarantees. So the same thing with return periods. If we talk about a 1 in 50 or 1 in 100 year return period event, it doesn't guarantee such an event is going to happen, but we're talking about the probabilities and how often you would probably see such an event happen. And then, very quickly, based on that choice of scenario, we can generate detailed flood maps anywhere on Earth. Now, within the tool, you can look at adaptation, and we're going to look at some examples of that later on, whether that's detailed local adaptation, like here, where we're editing a stormwater drainage system, the capacity of the drainage system and the inlets, or whether it's at a larger scale, where we look at flow rates for urban subcatchments, look at the hydrographs, the flow rates as they go up and down during an event within the basin. And then we can quickly sketch and design also local descriptive adaptations, like adjustments of land use and infiltration through adjusting forestation or green waterways, or some kind of adaptation to the stormwater drainage system for larger areas. And we can directly compare them side by side, looking at the values, but also looking at the differences that you see, so how much of a reduction we see in flood depth. Then in the tool we deal also with exposure, where we can look immediately for larger areas even at how many people, how many buildings, and how many length of road is going to be impacted by this particular simulation that I've done. Now we use global and satellite enhanced data sets of buildings, OpenStreetMap based data on road networks, and then the WorldPop global population data sets to estimate these numbers for rapid impact based forecasting. And as I mentioned before, we can do also forecasts, so global forecasts of the flood dynamics within any area on Earth based on global precipitation forecasts. Okay, so now we have sort of this modeling system, and I'm inviting you to try this out as well, and just look at some areas, look at some particular scenarios that you might find interesting. I wanted to specify also to some detail what is some of the input data that goes into this. Also to give you a little bit of understanding about the limitations that a modeling system like this has. And physically based models, anyway, models that relate to dynamic events on the Earth's surface are generally very data hungry. So there's multiple layers basically to the Earth's environment that we need information about to deal with that in an accurate way. The core of that, typically for flood modeling, is elevation data. Elevation data provides information about the most important guiding forces on the water, which is the gravitational and directional flow that is guided by the elevation itself. And the quality of the elevation model makes a big difference also on the quality of the flood model output. Now the same is true for some other data sets like channel information or things like urban and stormwater drainage or the infiltration capacities that the soil has. But typically we see most sensitivity and quality to the elevation data set. Now, for some of these, like elevation, we're able to merge in seamlessly high quality, high resolution data sets that are available at a national level. So we are now using some of our custom filtering and interpolation to deal with elevation data sets at a global scale. So that's some processing on top of Copernicus 30, which is a global space-based elevation model. But then for over 20 countries, we're now doing also 1 meter resolution LiDAR data, seamlessly available directly within the tool. It makes generally a big difference how you deal with elevation data itself, whether you do a certain type of interpolation or pre-processing to try and squeeze the most detail that you can out of the data itself. We see that noise filtering can help there. Noise filters remove unwanted errors in the elevation data, but they do always tend to smoothen the data and remove some of the detail that is there. Often DTM filters, terrain model filters that are meant to remove buildings and vegetation are applied. And there's a particular reason there. Often when you're given elevation data that is a surface model, in the sense that it includes both vegetation and buildings, you see that the buildings and vegetation or cars start to act as obstacles for water flow, while in reality the water is able to flow through or past them, although with some resistance, they're not able to fully obstruct the water flow. And that's where filters come in very handily. Now, we also apply such a DTM filter for the Copernicus global elevation model, which is a surface model, whereas the LiDAR datasets at a national level are terrain models by default. Just to visualize a little bit the quality difference here, we're using some previous generation global elevation model called SRTM and LiDAR elevation, both at the same resolution. So every grid cell within the model here is 10 meters on both sides. But it's just that the general accuracy, the vertical reliability of the elevation data for LiDAR, for the laser scanning based elevation model, is so much better that it's world apart in terms of its flood impact prediction in this area. Right, so level of detail and resolution doesn't say everything. It's also, do you have the data to effectively use that and benefit from that level of detail? And their LiDAR laser scanning based elevation data sets can make a big difference. For many other data sets, there's heavy use of global and space-based data collections. Think about precipitation, products like the NASA Global Precipitation Mission. Think about even commercial products like Worldem Neo for elevation. There's also global collections of soil in the soil grids product that we use for estimation of infiltration rates. There's satellite-based estimation of land use classes and NDVI for land cover and the effects that that has on the hydrological behavior of the area. Now, we also deal with AI bias correction of some of the climatic data sets, in particularly flow boundary conditions and precipitation. Here we deal with a global collection of hourly precipitation stations and daily discharge stations to correct the globally available gridded data sets that we require to provide global coverage. Now, there's about 16,000 stations there combined in total, most distributed above about Europe, North America, Japan, Australia, and then less but still a sizable amount in Asia, South America, and the least in Africa. What we're able to do there is provide a bias correction, so sort of a corrective nudge to our globally gridded precipitation extremes in order to provide more detail, but also to deal better with the accuracy of those gridded data sets. And here we see that our R values go from 0.6 to 0.864, a major increase as indicated by the scatter plots at the bottom right, as well as the deviation histograms at the top there. And generally we see that the bias correction procedure there is able to improve the match between the observation station data and the global gridded data set significantly. A similar thing is done for global river data. As I mentioned, we need to be able to determine whether a large river or small river stream is coming into a model domain to deal effectively with any domain that the user might specify. And there's a specifically customized global river database featuring splits in rivers with consistent attributes that we utilize to both estimate at a very local level boundary conditions and also deal with detection of incoming flows for any region. And you're looking here at some of the particular zoom-ins of that global data sets of rivers. There's also a built-in support for climate change scenarios, and this is based on global climate models. Now, the CMAP6, the Climate Model Intercomparison Project, was downscaled statistically by NASA to a consistent 25-kilometer global grid for about 20 different models. And this is key because the way that we approach this is very much in a fundamental level of insight, where we not just take a single model, but look at all of the different ensemble models and do a full extreme value analysis along the future periods for each of the ensemble members. This allows us to look at relative changes in extreme precipitation for different climate scenarios, different periods in the future, but also different types of events. So we get unique changes within the probabilities for shorter floods, longer floods, or maybe for lower or higher intensity. So we don't work with single ratios to go from current to future climate, but look at full PDF histogram transformations, as it were. And that allows us to also give uncertainty ranges to the impact of climate change on extreme precipitation intensities. And you can directly visualize these also in the FastFlood Global platform, where we show some of the climate analysis data and the uncertainty ranges around that between the 20 ensemble members of the CMIP6 project that we analyzed in full. Here you're looking at precipitation trends for Sri Lanka, and then you see 4 different models, and the shaded areas represent the 15th to the 85 percentile range within the ensemble of models. And here, particularly noticeable is that we see a stronger increase in flash flood intensities going into the future, with up to 20% of increase in rainfall intensities for 24-hour duration, while for longer, lower duration floods, the 5-day events, we see a reduced intensity increase up to 112 to 113% of the original current climate values. So this shows a little bit, some of the data and the methodology that goes into this flood model. I want to quickly cover also some of the example applications that we've done in the past years to both validate, calibrate the model. And we've been working heavily with partners to apply this technology to deal in a better way with flood information and the interactivity around it. Just 4 examples here that we've worked with. Flash flooding, for example, this is the on the top left, the flood event in 2023 in Derna, Libya, where we saw a major flash flood combined with a dam disaster impacting thousands of lives in Derna. A fluvial flood event, a smaller river basin, somewhere between flash and fluvial floods in Valkenburg in the Netherlands along the Geul River. Then Jordan Valley, we see a dam break event also impacting some urbanized areas. And finally in Mauritania, we see coastal flood events happening along Nouakchott. Now we use the model a lot for rapid assessment during, before, and immediately after a disaster, as we're able to provide flood information very rapidly during such a disaster. So here this is one of the applications we did, where we looked even before the event at predicting within 15 seconds for the entire Jamaica a 20-meter resolution flood map based on the incoming tropical cyclone forecast from the ECMWF data. Now we're able to provide global high detailed flood forecast with this rapid tool, and often later we look at validation using satellite data. You see here the Copernicus Emergency Management Service maps, where they looked at commercial satellite data that they publish for these disaster-struck areas. You see mostly how the satellites pick up a lot of the water that pools in lower lying areas, and often miss a lot of the smaller streams and flash flooding because the satellites fly over, not during the exact timing, but often a day or so later. And then some of the smaller streams are already subsided during these short duration flash flood events. We did a lot of reference studies compared to full traditional physically based modeling. Here you see an application of that in the Caribbean, in Grand Bay in Dominica for the impact of Hurricane Maria, looking also at observed flood extent, and then a reference simulation done using LISM, which is a more traditional industry standard full Saint-Venant equation solver. A little bit more detail about this case study in the Netherlands I mentioned, in Valkenburg. This was a flood in 2021 in the south of the Netherlands, with quite some financial impact and luckily no casualties. There was a severe sort of flash flood event for most of the region there, including parts of Belgium and Germany and France, where there were significant casualties as well. We use here the 5-meter resolution national LiDAR data that's built into the platform, and it runs for the entire basin in several seconds. This is about 250 square kilometers of surface area. Leveraging the radar precipitation data, the national data sets on land use, on soils, and on elevation models as well. And you see in the image there the FastFlood output together with the red outlines, the black outlines representing the observed flood extent from the survey done by the government after the event. We did a similar thing here. We're using space-based data in the Ishim River in Kazakhstan for the snowmelt-driven floods in 2024. So you're seeing here on the right the satellite imagery during the peak of the floods obtained on the 11th of April with the red outlines, the automatically detected flood extent, and on the left you see those red outlines compared to the flood depth prediction from FastFlood. Recently we've been doing a lot of comparisons and validation using HECRAS as a reference in urban areas in Canada, dealing also with water management infrastructure in automated ways. Getting also here excellent results in terms of flood extents and depths along the river. Some of the other disaster-related applications that we did very recently here, this is Maputo in Mozambique, 10-meter resolution simulation we did for the February and January flood events in 2026. Compared again with Copernicus Emergency Management Service observed flood extents. And there the data was available for the bottom left corner of the image here, showing an excellent match, whereas the satellites of course missed some of the urban smaller streams that subsided by the time the data was acquired. And a similar thing at large scale. So this is the entire country of Sri Lanka, where we modeled the fall 2025 flood event as well, comparing with ICI satellite-based flood extent estimates. If you have any questions on this, you can always reach out to us. You can find our contact information on our website, and the tool is available for you as well to try out and get informed about flood information, risk, and potential solutions within your area. Now, for the final phase of this, I want to have a quick look with you at some example applications of the model and guide you through some types of simulations that you can do with the tool. So I'm going to open up the website, fastflood.org, and you can go there right now to follow along as well if you like. And I'm going to click on FastFlood Global here, which opens up the FastFlood Global platform. Now, in principle, it's as simple as selecting your location and then selecting a scenario that you would like to see. And you can do this globally. You can also close this welcome screen and just click an area on the map. But for now, I'm going to select our office location in Apeldoorn in the Netherlands. And I'm going to select an extreme event, which is a 1 in 100 year return period flood event. Now, everybody is able in principle to do simulations daily for free. It depends on your IP address. And then you'll get a message when you've run out of free simulations for the day. So we're starting an extreme scenario here. And then we're going to have a look at some of the output there. There we go. So this is a 1 in 100 year return period event. These are quite extreme events, right? These are very rare with severe precipitation as a trigger. And we see for the locations that I am currently on with the marker, and I can move that marker, we get about 40 centimeters of flood depth in this particular street. Now, it gives a rough estimation of what the potential impact and consequences could be there. These are based on some of the national guideline documents that are available, but they differ, of course, in your area, right? Some areas are more used to and therefore also more resilient to flood impact than others. Now, at the top, we see the button Add Change. And using that button, we can start to add various changes to the scenario that we're running here. That could be barriers, that could be nature-based solutions, that could be, well, there's a whole bunch of options there. For now, I'm going to select Add Adaptation. And I'm going to click on the polygon area here to select a region for which I want to perhaps make some kind of change to the model. So let's take the area in the south here. And let's say we're going to take this one and take this city block and look at the potential impact of maybe a stormwater drainage system with higher capacity. We can save those changes immediately once we've selected them. And then the option to rerun the simulation appears at the top. I'm going to click that. And it will run the exact same scenario, but with the addition of the changes that we've made to the model here. Now we'll get back our new flood map in a little bit. And then at the top we see the button Compare Simulations. And we can do a direct comparison side by side of these and look at the different flood maps. Now we see on the left the changed one and on the right the original one. Now this is quite a severe measure that I input and it's very effective, although it would be quite a costly one to implement at that level of capacity. And we can also look at the differences between them and see how this is gonna reduce and also downstream result in a severe reduction in terms of flood depth. If I right mouse click, you can see that for several locations, even downstream, we see reductions up to 30 to 50 centimeters of flood depth. Now, perhaps another simulation that's interesting to highlight here is a dam break event. If we click anywhere on the map, we can go ahead and click on Custom Simulation, and then there is the dam break option. Now this shows to you a global database of dams, and we can go to one and select it. And if we click on it, we can start to do a dam break simulation. Now by default, it's going to fill in the properties here based on these global data sets. And there's a whole bunch of options you can get into on the documentation of FastFlood to see what they mean. For now, I just wanted to show you that you can also specify yourself the height. Some of the data in these global data sets are not always fully reliable. And then if you want to run the model, select Run. And it's going to automatically select the domain around this and then allow you to run a dam break event based on that input. There we go, and we see the downstream impact going to the Mediterranean from this simulation. Now, we run this model for small and large areas. Like I said, often using national high-quality data sets if we can. Just to show that some area here near New York, I'm going to click on an area along a river here and select Extreme Event just to showcase. We can automatically see some of these discharge boundary conditions do their work. And also the usage of these high-resolution LiDAR datasets. Now this is giving some severe flooding in a 100-year return period in the streets next to the river here. If you click on the top left of the tool, you can see some of the simulations that you've done. Now there's a couple tools that are useful there, and for this particular simulation, I'm going to give it a new name. New York. Let's go through these one by one. The first one allows you to toggle the actual flood map itself. Now the second one allows you to also visualize the river network. And if we do so, we see the major river here, and then we can click also on the river network to see the hydrograph estimations and the peak flow rates. And the same is true for some of the smaller streams. Now I'm going to remove that layer again. If we click on the next one, we get an overview of all the layers that are available from the model, from flood depth to velocities and discharge, the terrain, etc., etc. And you can visualize these, and you can also download them as GeoTIFF files. One interesting one here is the water sources layer. This shows you the discharge boundary conditions automatically placed by the model, and if I click on them, I can also see the level of discharge that's provided for this scenario. Finally, there is the Edit button on the right, where we can do more detailed changes to various types and aspects of the model. For example, we can input a climate scenario into the model, specify the type of scenario and the period that we're looking for, maybe 2090, apply that scenario, and then if we click on Rerun Simulation, we can rerun the scenario with climate change applied to it. Now, we deal with small and large areas. As I said, what might be interesting is to have a quick look at some bigger area. Maybe if we go to the top right and select Add Area and then Select, we can go ahead and select any domain. And then for the hazard map option, by default, it goes to 50-year return period, and we could specify the level of detail that we're interested in. For now, I'm just going to click Run, and it should generate for us, for this entire area, a 50-year return period flood hazard map. Once we've done that, we can look at some of the additional analysis tools that are there in the platform as well. For now, if we right mouse click on the map, there's a couple options under datasets that are interesting to look at here. You can visualize the historic rainfall statistics for any location. These are IDF curves that represent the probabilities and the intensities, how often these kind of extremes happen in this region. There's also the option to see forecast or even the climate trends that I mentioned earlier during this lecture. We can also see some of the station data that we use globally to train and verify the behavior of the model. So these are locations within this area, and as I said, most of the points are concentrated in the Americas, in Europe, and Japan, and Australia, but there are a decent amount of global points available. Where for every point, we can also see the frequency analysis of the discharge within that point, as well as the IDF curves for rainfall stations. Now, for our model, we need discharge boundary conditions everywhere, and we can also visualize and inspect those conditions based on the gridded data sets. And if we click along the river somewhere, we can see the extreme flows and also export them for any other locations. And typically, and here as well, we see that there's an excellent match between the station data and the discharge data within our gridded boundary condition data sets, often within a several % deviation range. Now, the simulation was already done, as you might have seen. There are some additional analysis options if you click on the 3 dots for the simulation entry. If you go to Analysis and then Analyze, you can see flood stats, so how much area was covered with what water depths, the water balance, so how much infiltrated, how much rainfall did fall within this area during this event. A flow velocity field that allows you to see the peak flow directions and velocities as well. And exposure data, although for bigger areas, this tends to take a little bit as it needs to deal with individual building and road level data for large areas. I've hoped you found this useful. If you have any questions, you can reach out to us. You can find our information and the model documentation either on fastflood.org, where you can click on the documentation, or on the showcases to get more information there, or on fasthazard.com, where you can find our contact information and more information about us. Thank you for watching, and I wish you all the best of luck in your modeling efforts.